So tonight we'll talk about astronomy camera controlled as a computer network, computer network controlled, computer numeric controlled router. I'll get it right. So as you can tell from looking at some of the presentations, I'm a big fan of repurposing, as in take this, it wasn't meant for this, use it for that. For those that weren't that familiar with Ioptron, they've discontinued all of their low-end cube altitude azimuth telescope mounts, which I thought were great entry-level GoTo telescopes. They were not expensive. They were very reliable in quick setup and pointing, and you could use them in the daytime. You didn't need to see Polaris. It was great. And now they've got all these replacements out there from Orion and Celestron, which are kind of the same, Cinta and Skywatcher. And none of them could hold a candle to what the Ioptron cubes could do, because first off, none of them have a built-in GPS. The second thing is, two of those three, the one from Cinta and Skywatcher, do not even come with a hand paddle. Oh, you'll just use your mobile phone over Wi-Fi. That just made things so complicated. So I said, well, why don't we take a look at pan tilt zoom cameras as a complete replacement for the camera and the telescope. Well, first thing we found out was the zoom level is insufficient, and there's no integration for astronomy applications, and somebody would have to write some software to write a driver to make the camera talk to astronomy applications. That's the ND to ONVIF driver. So the next thing we looked at is, how cheap can we go? The pan tilt light bulb cameras. I've still got one of those. It's right now my front porch direct down camera. So when something arrives as a shipment from Amazon and they leave it on my doorstep, I've got a live video camera pointing down at my front doorstep so I can see if it's there or not. Those cameras, while inexpensive, have no zoom capability. There's no analog zoom. The zoom is all digital, so you're limited. And I said, I'll swap out that wide field view with a narrower field view. And then what I found out was the pan and tilt motors, when you nudge it to move, they move a large number of degrees angle, which means you'd have gaps in the viewing. So that's not a solution. So I said, well, I own a low-end computer numeric controlled router. I know what the internals look like. So why couldn't we use one of the do-it-yourself CNC router kits as the basis for a low-end altitude azimuth telescope mount and astronomical imaging camera focusing in zoom? So that's what we'll focus on. So as I've also pointed out, you don't have to buy a packaged product as long as they physically work together. You can go buy your telescope from Orion and buy your mount from Ioptron, and Vixen style dovetail. They'll work together, no problem. So you don't have to buy everything from one manufacturer. And some of the newer companies have taken that to the extreme. There's a slide towards the end regarding that. Just because you prefer a branded product from a manufacturer doesn't mean you have to buy everything from them or even from them as the seller. I've often found things that were less expensive that were exactly the same product without the brand name on the outside of it. So look for street prices, look for free shipping. If you're already paying for free shipping like Amazon Prime, then they're going to bump the price up a little bit, but nowhere near to cover $20 to $30 on shipping. And do look for things from the original equipment manufacturers, not necessarily from the brands. And remember, what you thought was a separate brand may no longer be a separate brand, as in Cinta has their hooks in Celestron and Orion has their hooks in Meade. So when you say, I don't want to buy an Orion mount, I want to buy a Meade mount. Well, your money is going to Orion whether you like it or not, because Meade was acquired by Orion when they went bankrupt. Steppers and servos and DC motors, this is where it starts to get a little technical. There's basically three kinds of motors for moving things around. A DC motor, or sometimes also referred to as a servo motor, but slightly different. A DC motor is what they put in those light bulb pan tilt cameras. So when you say, move it a little bit, you turn on the voltage, the motor turns, you turn off the voltage as quickly as you can, and the motor goes, and slowly comes to a stop. So when you say, go one step is not a small number. It might be 15 degrees. So DC motors, no. Servos, a little bit different because they'll typically know where they start and know where they end. They'll have limits on them, and they'll be more precise in how small an amount of voltage you can deliver over a period of time. But they still have limits on when you say stop. If somebody bumps it, it can move. So there's no locking. Steppers are more like, I'll only move this much angular distance every time you give me a pulse. One pulse equals 1.8 degrees or whatever. So now you have to think about gearing to get finer resolution. Indexing, where is it right now? Well, you can either have encoders, which means as it moves, it's actually signaling pulse, 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 to let you know when you count the pulses, how far it's moved. And then you have limit stops where there's an indicator that says you're at the beginning, and you bump up against that and say you're at the beginning, and then you just run it until it gets all the way to the other end, and you time the amount of time you've moved the motor until it gets to the switch at the other end to say, stop again. And then you divide that up, and that's what your movements are. So servos tend to be cheaper than steppers, but steppers tend to be the better way of doing things. So if we had to compare, well, I've got this router thing that has a computer and a couple of motors on it. How would that compare to, let's say, an altitude azimuth telescope mount? Well, let's see. The telescope needs to move in pan, so horizontally 360 degrees. Tilt, or elevation, altitude, has to move up and down. Focus, because we want to automate the focus knob. And then zoom. We need some way of saying, I want it more magnified. But if you do this on the low end, as you change the zoom, you also have to adjust the focus. So we'll need to be able to move both of those, focus and zoom, in fine increments. How does that compare to a CNC router? Well, we've got a similar number of motors if you get the kind that have a second y-axis. So x-axis, y-axis, z-axis, and they have newer ones now that if you're etching or doing something like you want to put a text on a bottle, you need to rotate the bottle in roll. And as you rotate it, you need a motor that does that too. So you'll find that the ones that do pitch, roll, yaw, and rotation will give you your 4 motors. And they have pulse wave modulation, so you can do all that fine increment movement stuff. And they'll have the ability to have fine movement in plus or minus directions and continuous movement. So it's got all the right movements, and it has the right number of motors. But you'll need to buy the version that has the limit switches so you know where the beginning and the end is. So this looks kind of same old, kind of similar. The motors are called NEMA 17 motors. Those are very typical. They're stepper motors. You give it a pulse, it'll move a certain angular rotation. It has a certain torque that it can do. So it'll be able to move a certain amount of mass without any gearing whatsoever. We need to be able to move the telescope accurately, reliably, and with high precision. And we just need different angles and directions and speeds. But that can be mapped. So far good. So far, so good. So how do you talk about moving these things? Well, for your router, there's a computer board, a control board called Gerbil, GRBL. It's running that software. It's on an Arduino-like control board, and it runs something called G-codes. G-codes are the programming commands you give your router to say, now move over here, move up or down this amount, turn the spindle motor on, and make it spin at this RPM for this period of time as it cuts into the material. And then you turn the motor off, you raise up the spindle, you move it over somewhere else, or you leave the spindle motor running, and then you just sort of pull the spindle motor along in a direction, and it will cut for you. So G codes are the commands of making your router route things. Well, we don't need G code for astronomy, but we do need INDI. INDI is for astronomy what G code is for routers. It says, move to this right ascension declination or move to this altitude azimuth. And once you're there, start tracking at this speed. So that's what INDI does. So we need something that will map things to things, like we need something that will take the astronomy planetarium software request, which is going to command in INDI, and we need to map that to G code to talk to the gerbil. A telescope mount plus a camera is not a CNC, so you need something that will gateway or map from what it is to what you want it to do because you're repurposing it. So what don't we need? Well, if you buy one of these really priced, reasonable packages called a do-it-yourself router kit, some assembly required, you get a whole bunch of parts, and then you have to assemble it to make your router. I mean, there's no cutting or soldering you have to do. Everything is just you sort of bolt together. Takes about, I think, I built some of these things before, so it took me roughly an hour. So I'd say first timer, hour and a half to 2 hours tops, and you can put it together. You put it together, but you don't need some of these things. For example, you're building a telescope mount. You don't need the router frame. You don't need the router bed. You don't need the spindle motor. You do need all the motors. You don't need the threaded rods. So there's a lot of it you can throw away. But if you buy it as a kit, you can get the whole kit and caboodle for a reasonable price. So you're going to be throwing away a lot of stuff from the CNC router kit that you don't need for the telescope mount. The stuff you need in addition, you've got a motor. You can actually buy short body motors that take up less space. So if you wind up just buying the individual parts because you don't want to throw away all the other router stuff, go for the NEMA 17 style, which is the dimensions and the shaft and the torque are where you get that NEMA number 17. But the coupler that is used as a coupler to hook the shaft onto something else you want to turn, those are all standard. And when they rotate, you give it a pulse and it rotates 1.8 degrees. So if you want it to be turning at some other speed, like, I don't know, you want to do sidereal movement because you want to do a tracking, and the tracking turns out to be other than 1.8 degrees, you're going to need a geared belt drive or a meshing gear mechanism. The control board, this is kind of the top end control board, still under $100. It's amazing you can buy this much computational capability with this many different channels of controller, and it's under $100. But this is a 6-axis. You don't need a 6-axis, but 5 would be good. So there's 2 ways you can get it doing 5. You can either buy something that just does 5, or you can buy something that does 3 or 4 and buy add-ons. And here's how you do it with add-ons. There's a thing called CAN bus, Controller Area Network, and you'll actually find these in your car. So when, for example, your windshield wiper motor would like to run at a certain speed based upon you rotating a knob on the stalk, when you rotate the knob, it goes to a computer in your car that will then send commands to one of these CAN boards that's basically bolted onto the windshield wiper motor. So how many wires do you need going to the windshield wiper motor? 4. 2 for power, you have power and ground, and then 2 for data. And then how you make the motor move, the speed, the timing, all that stuff can now be abstracted. So you don't need to run like 8 wires to the windshield wiper motor. So that works for both your front windshield wiper, and if you have an SUV, the rear windshield wiper. So you can reuse a lot of this stuff. And there are companies that do this for CNC routers where if you want just a motor controller, they'll put it in a metal case for you, and you can buy a CAN module just for the motor. But more likely, you can buy these cheaper. You buy basically an offloading CAN board, and it has the motor control, some parallel input-output pins, some signaling pins, additional voltage inputs, and this is just one board. It's like $46. So you can CAN bus distribute these things. So you might just buy a CAN bus based controller and then buy for your altitude and your azimuth and then your zoom and your focus 4 CAN boards. The total might be more, but it's much more modular. So think about it this way: coordinated movement. If you're doing a router, you have to have coordinated movement. The spindle will turn the motor on and then go over here and move down, and then you want to draw a circle, you want to etch a circle, it's going to have to move in X and Y appropriately. And then if you say, as it's doing that, I actually want that route that it's cutting to go from shallow to deep. So it's moving the X, moving the Y, moving the Z, and adjusting the spindle motor all at the same time in a coordinated dance. Telescopes don't do that. You might move in altitude and azimuth at roughly the same time, but they don't have to be lockstep with one another because you're going to move probably in azimuth a larger number of degrees than you are in altitude. So it's cool to watch it moving in 2 directions at the same time on your telescope mount. Doesn't necessarily need to, but it'll take less time to get there. I've seen some of the early Orion GoTo telescopes go, okay, I'm going to move in azimuth. And then when it gets here, it goes, I'm going to move in altitude. Looks very hokey. But if it moves in azimuth and altitude at the same time, and it roughly stops both motors at the same time, it looks really cool. Plus, think about it this way. If you're moving in azimuth, as you're moving, you accelerate, and then as you get to the end, you decelerate. That makes the amount of play in your mount build up and then let go. You get slop in your gearing. But if you're moving azimuth and altitude at the same time, it almost cancels out the slop because you have 2 forces at 90 degrees to one another. Just a weird physics deal. It allows you to make cheaper gearing. And there's some motors you just can't move until you're there. So if I want to adjust the focus and the zoom, that doesn't really work until I'm actually at the target and tracking it. So I broke it down and said, okay, what if we just said controller, a CAN controller interface board, and then we got multiple CAN microbus controllers for altitude, azimuth, zoom, and focus. This is the entire electronics for the telescope mount. It's a Raspberry Pi 02W, about the size of a piece of chewing gum, a stick of chewing gum. And then you have a CAN bus interface board that piggybacks on top of that. And then you have 4 wires going daisy chain to each one of the controller boards. This is actually, it's not CAN bus, but this is actually how the low-end, low-cost Ioptron SmartStar cubes work. They have a different controller board for altitude and azimuth. CAN, but which CAN and which CAN product. So there are multiple versions of the CAN bus. They run at different speeds and such, and they're usage appropriate. CAN dates all the way back to the 1980s, which is why cars that are 10 years old would have a CAN bus in them. But they've got newer and faster ones. So we would probably be running the CAN bus that runs at up to, a megabit or so, and is long distance. The one that runs at 500 meters or 1,640 feet is more than capable of doing any telescope stuff that we've got. And you want it to run at 12 volts because that's kind of a normal inside telescope mount. So, but even if you goosed it up and said, let's get the C version of CAN bus that'll run at 8 megabits, that is not enough for your imaging. So your imaging will still be over a USB connection or a Ethernet connection because you need multi-megabits. So if your stepper motor doesn't run at the speed you want it to run at, what you need is gearing. You need to make fast, slower, slow, fast. So what you'll find is for your azimuth, you'll have a very small worm gear that can very precisely rotate the mount to a fraction of a degree. And then for your elevation, for your altitude, you'll have the same thing, but it'll probably be a belt drive because that just takes up physically less space. And if you want to do focusing and zoom, that might be even a direct drive because 1.8 degrees, when you can do 360 degrees continuously on your focus knob, 1.8 degrees is plenty small. But these are off-the-shelf gears, off-the-shelf belts. You don't have to go, hand make anything. And the cool thing was, if you want to rotate the zoom on a zoom lens, you get a piece of this belt material and you cut it, wrap it around the outside of the zoom adjustment, glue it onto there, and then you have the gear actually engage the belt from the outside. So it'll rotate the zoom. Here's some of the issues you run into whenever you have to deal with gears and belts. When something's sitting still, it has inertia. And then you have to crank up the motor to break the inertia to get it moving. Once you have it moving, if you've got a heavy weight like a telescope and you move that up to the zenith and then you go past the zenith, the weight actually changes. It goes from a heavy load to no load to a heavy load in the opposite direction. So this changes the weight on your gearing. So you have to deal with that's a little slop, a little backlash, but it is what it is. You can always move it back the other direction. When you go to stop the movement, you've got this heavy thing moving. Now you're going to just suddenly stop it? No, you've got to slow it down right to the stop point, and then you may actually go a little bit past it and bring it back, and now it's stopped. But if you don't bring it back and then stop it, you'll actually have backlash in your gearing. So you have to pay attention to those kind of things. So here's the big picture of the software. The image on the top right is really what you want to focus on. You've got your planetarium software and your imaging software. And you can see there's stellarium there. An open source free copy of imaging software is something called ECOS. It's by the same guys that brought you K-Stars, which is a free open source competitor to stellarium. So you've got the planetarium app and it controls the positioning of the mount and the focuser. And then you have another app that controls exposure, number of shots, durations kind of thing. But all of that comes into the ND server. And the ND server has different channels for doing things. And you'll find that the mount and the focusing will go off to a new piece of software that has to be written called the ND to G code driver. So that runs your motors. And then you have another piece of software that is the ND to camera driver, and that'll run your camera. So that's the two pieces of software that need to be created. I know, I'm a software guy. I'll just go, yeah, I'll knock that out. But it takes work. So as I mentioned, if you wanted to roll up a computer that would do all this stuff, you could go buy a packaged gerbil controller, but now you've got to adjust the gerbil software to do astronomy things. It's much easier to turn it the other way around and say, well, I'll take something off the shelf that I can probably run some Python or something in like that. And that will interface with off-the-shelf astronomy software. And then I'll just have the driver map, the ND software commands to be G-code commands. And now I can reuse my G-code controller. So there's slewing, nudging, and tracking. These are the three means by which motors move on a telescope. Slewing is like, I want to go to the moon. And it starts off and it moves at a high speed, and then it slows down and it gets to the target. It thinks it's at the target, but then you look in the eyepiece and you go, you're a little off. And you push the buttons to nudge it a little bit. And just as soon as it gets on target, it starts tracking. It goes, you said go to the moon, I'm going to lunar track. Or if you said go to the sun, I'm going to solar track. Or if you said go to some deep space object, I'm going to sidereal track. So different speeds of tracking. And if things are not perfect, you might want to nudge it, give it a little bit of movement. And so you have to deal with that from motor commands. You have to have a mapping table that says, if I'm going to be slewing, the G-code command will be run the motor at this speed. If you want to nudge it, it's a different speed. And once it's tracking, you have three different tracking rates that you're going to be dealing with. This is for the person that gets bold and daring enough to implement the mapping driver. So when I post this to the public on the YouTube and somebody goes, hey, I watched your video. Yeah, I built one. You want to see it? Yeah, I'd like to see it. And here's the packaged versus components. This is the complete opposite end. You pay a lot more money than you should, and you buy a lot less telescope than you think you're getting, but it has a camera, no eyepiece, and no hand paddle. And it looks really simple to run, but it's very forgiving because it's an inexpensive refractor that has a very wide field of view. It does not zoom using lenses. It zooms in software. So the camera has a lot of megapixels, and the way you zoom is by cropping. But you tell it to zoom, and all it's doing is it's throwing away pixels. Think about it. If I have a target, like let's say the Pillars of Creation, which is part of the Eagle Nebula, but it's very, very small. I take my 8 megapixel image of the Eagle Nebula, and then I go, I want to zoom in on the Pillars of Creation. And so all it's doing is it's cutting off all the pixels around the pillars and showing you just a magnified image of the pillars. And when you zoom in to a certain level, eventually it's going to become a little grainy, a little pixelated. But that's how they zoom on these things, with no zoom mechanism whatsoever. So I'm not, as you can tell by now, I'm not a big fan of, paying over $2,000 for a what amounts to a low-end optical instrument that somebody's thrown some software on. And, you may want to use it in an automated fashion, but you may want to well, let me stick an eyepiece in that thing. There's no hole for an eyepiece. The camera is built in. I like that telescope. Oh, I'd like to put a replacement telescope on there. There's no Vixen dovetail plate. It's bolted in. That's the telescope you bought. That's the telescope it is. Well, it's a little off. I'll use the finder to get a better adjustment. No. It's looking at a wide field. It does plate solving. So if the sky's too bright, or if it's not quite on target, it can't align. Try again. Okay. And then what if you want a different camera? There's no ability to remove the camera, replace it with like an upgraded camera. So it's a packaged product. You paid extra to get what you got. So we decompose it. Here's a good telescope. This is the one I actually took with me to Cape Canaveral. But it's on a Vixen dovetail plate. So you can loosen this knob on the top, and you can take this stand off and use the stand for other things. It has a finder on it. It's got a red dot finder, but I took out the red dot finder. I put in an optical finder with a right angle on it. I'm happy. It's lightweight, but it gives you high magnification. So here's how I made it better. I took off the red dot finder and I put a right angle finder on it. Notice it fits in the same plate, same mounting bracket.
Don't think it's better.
Well, you have to get used to the fact that it's right angle, but the fact that it's got actually a narrower field of view. The red dot finder has 0 magnification. And once you get older and you don't enjoy bending down to look straight through the red dot finder, yeah, the right angle is comfort city. So here's a mount. This is a manual mount. It's actually an Orion mount. I used to like the Celestron manual mount. And then I found out it's got some shortcomings. So I said, well, I don't own one of these currently, but it looked promising because it has manual knobs for adjusting it. So if you want to unlock it and just arbitrarily point it somewhere else, it's got a knob on the side for elevation. It's got a knob on the bottom for azimuth. You can unlock it and position it wherever you want, lock it back, and then you can use the 2 control knob stalks for fine adjustment. Well, I'd take the control knob stalks off, I'd hook on my NEMA 17 motors, and now it's good to go. I can manually move it, or I can let the computer motors move it. What I didn't see from this is it has a limited range of movement of about 30 degrees. So you look down here and you think, well, I can move 360 degrees, right? No, there's a worm gear down here, and there's a limited number of teeth on the gear that it meshes with. So it can only move like plus or minus 7 degrees. You want to go farther? That's what the big knob on the bottom is for. Aw. But it's nice. It'll carry 11 pounds or 4.99 kilograms, 5 kilograms. So it's an inexpensive mount. You add the computers, the motors and stuff. So how would you make it better? Well, I went looking and I found the Skywatcher mount that doesn't come with a hand paddle, but it's got a Vixen dovetail plate. And I found this very strange thing from Celestron. Doesn't come with a hand paddle. You can't even buy a hand paddle for it. But it's very small and compact. And they still have the nerve to charge you $300 for the damn thing. So, yeah, I'm not a fan of that. So what about obstructions and wiring? If you have a long tube refractor and you want to tilt the telescope up at a high angle, the bottom of the telescope is going to hit the tripod to hit the top of the mount. Let me show you something here. You see this angle? Why the top of the telescope is off at an angle? It's so you can have a very long tube telescope that won't hit the mount or the tripod legs. That's why it's at an angle. See how far back it is? Make note of that. Now let's go here. See this mount? This wonderful thing that Celestron's charging you $300 for? Imagine you have a long tube refractor. You want to get vertical with it, it's going to hit a tripod leg. So that's why what they call one-arm bandit type telescopes, the better ones are the ones where the top part of the arm is bent backwards. And that's why it's bent. But I want to move 360 degrees. Now, what you actually want to move is 720 degrees. Because if you can only move 359, 59, 59, that's probably because your wiring internally will catch, and it's not actually free moving. So if you can only move 359, 59, 59, how do you move farther? You do a thing called cord wrap. So as the mount's moving, it's kind of keeping track of how far it's gone. And when it realizes, oh, the next move I'm going to make, whether it's a slew or a nudge or guiding or tracking, the next move I'm going to make will take me past that stop, will take me past the danger zone. So instead of going this way, I need to go the other way. and it needs to do that in both directions. So that's the three-dimensional interwoven mathematics called topology. That's why I said, I beg your topology. So if we want to make the tripod better, maybe we start by making the base sturdier. The inexpensive Orion has a 1-inch tube diameter on the legs. A little shaky for heavier, if you want to put a heavier scope on it. So you can buy just a tripod that'll have a 1.5-inch, and going from a round 1.5-inch tube diameter, a 1-inch tube diameter to 1.5-inch really makes a big difference, because the tubes change from aluminum, which can be flexed and bent, to stainless steel. The camera and the eyepiece adapter. Well, if we're going to use a 3-megapixel security camera, you need to make sure you get the kind that have a lens that can be unscrewed from the front of it. And once you unscrew the lens, now you need to poke that into either an 1.25-inch eyepiece receiver, which is just called an 1.25-inch eyepiece. But the camera lens is actually a metric thread. It's an M12 by 1/2, also known as an S-mount. So if you can buy an adapter that is S-mount to something else, and you can buy 2 different versions of that. You can go straight to the 1.25 inch, or the one that's more interesting is the T-mount, which is an M42 by 0.75. It's a little coarser, larger diameter. That one will actually screw onto the front of a zoom eyepiece. So the camera, if you want to make the camera better, you would get a different kind of camera, or you put a Peltier cooler on it to reduce the noise level. So here's your zoom. Helen's seen one of these. You buy it as a zoom eyepiece, and you put your eye up to it. It's got a nice eye relief on it, and you grab that sort of knurled rubber collar in the middle, and you can rotate it, and it will zoom from 8 millimeters to 24 millimeters. But if you take the rubber off the front, it exposes a T-thread, and you can get a 1.25 inch to T-thread adapter and screw it onto the front of the eyepiece. So now you don't actually need an eyepiece. The camera can be parfocal straight into the zoom. So that's why you need that shorter adapter to give you better back focus. So instead of having this on the front of the eyepiece, you actually get this shorter adapter, and it goes straight from the camera, straight onto the T adapter, straight into the zoom eyepiece. So if you wanted to make the zoom better, you'd buy the $200 one instead of the sub $100 one. And when you zoom, it would stay in focus. That's called a parfocal zoom eyepiece.
Mine is not parfocal. I have to adjust the focus.
Yeah, so is mine. Mine is pretty much the same thing. I bought mine from Lumicon, but it's actually made by a Chinese company. So Helen's is a Celestron, mine's a Lumicon, and they're identical. And I paid more for the Lumicon because it's Lumicon.
But it looks like it was manufactured in the same place.
It probably was. They just, etched different brand names on it. If you could find one that had a wider zoom level so you could get even less magnification, it would give you a wider field of view, which is saying, hey, if I've got at least a 1/2 degree field of view, I don't need to do anything special for the sun or the moon. And with a 1/2 degree, I don't need a finder. I can just say, GoTo, and it'll get me within a 1/2 degree easy. So that would eliminate the finder, which is eliminating a pain, a setup. So as I said, here's my soapbox stand on prepackaged smart telescopes. They get a wide field of view, a multi-megapixel camera. Take out your eyepiece, remove your hand controller, and you get what you got, despite the fact that you paid more money for it. Okay, so when manufacturers don't make the products you want, you need to be resourceful. Repurposing is a way to accomplish this, but it's do-it-yourself, so you may have some work to do. consider decomposition or buying pieces from different sources or unbranded sources. When you're doing a do-it-yourself, success is not guaranteed. There may be some trial and error. You may wind up finding out that I really want that truly parfocal zoom because I'm tired of zoom, focus, zoom, focus. You know, you can upgrade parts, but if you buy it as a package deal, it is what it is. Be critical of what you've produced. Always note the shortcomings and find ways to make it better for yourself as well as the next people coming down the line. Anytime software is required to be developed or changed, that becomes an insurmountable hurdle for most people because most people aren't software developers. Low-end or dirt cheap altitude azimuth mounts with a camera require lots of similar capabilities to inexpensive desktop CNC routers. So why not repurpose the parts you get in a low-end CNC router and add a camera to it and create yourself a telescope mount? I think of that as a far more productive endeavor in amateur astronomy than the person who says, I'm going to grind my own 10-inch mirror. You're going to spend a lot of time when you could have just bought one off the shelf, or if you're going to do a 10-inch mirror and it's a spherical, just go buy yourself a Dob. Go buy yourself a 10-inch Dob. You'd be a lot happier because as soon as you receive it in shipping, you can go out and set it up and use it. You don't have to go, I'm still grinding my mirror, and then I'm going to send it out to be coated, and then I'm going to build a telescope body around it, and yeah. So building do-it-yourself does take time, and you may be able to buy an inexpensive kit out there that will get you most of the parts you need, because companies like Ioptron, you've got a lovely low-end mount. Why did you discontinue it? Well, because we started producing the more expensive ones, and they make us more ching, more cha-ching. Okay, more gravy, I get it. And I put some links out there that if people want to go look at individual stuff, they can.
The other idea that you can advise is that when you're working something specific, if you go to the forums online, it's like for every brand of everything that's being produced everywhere, there is a forum online or there is a video on YouTube. So look for the forums that is always people doing the same thing that you are doing.
Yeah, if you buy a particular brand or model of a product and you're having difficulties with it, even if it's stuff that you just haven't learned how to do it, yeah, there's brand forums out there, or there are independent forums not associated with the brand that can, basically somebody else out there's already had your problem and probably solved it. But if you do too much do-it-yourself, you just get a bunch of people commenting on, you took your CNC router, which was wonderful, and you've cannibalized it to make a telescope mount? Yeah.
Yeah,
that's when they roll their eyeballs, and then they unfriend
especially
the group.
You're going to piss out a lot of people, like mechanical engineering people, and a lot of people who like astronomy or physics or some stuff is like, oh, this is good, this is interesting. Oh, programmers, or like all the kinds of engineers. So you're going to be like two bands of people. Yes. You did a sacrilege, and you'd like, oh, I like this idea.
Yes, and all somebody needs to see is your cobbled together thing, a parts list and an assembly guide, and somebody else out there is going to try and do it, and they're going to point out everything you did wrong, and you should have bought this part instead of that part, and why did you buy it from this supplier instead of that supplier? But then you say, mine works. Does yours work yet? No. Okay. So yeah, repurposing and do-it-yourself does have its downsides, but when you got nothing but time on your hands.
You should use the I Void Warranties t-shirt for this recommendation.
Yeah, not only void warranties, I tear products apart, and I take things out of them and reuse them for things they were never intended for. But, you know,
I don't know. Probably everyone in this forum here probably went to Lowe's or Home Depot, and then some poor thing comes and talk to you. Would you like some help? And you go and look at the person. I don't think so.
the way they phrase it always, welcome to Home Depot. Can I help you, sir? No, I don't think so. Or when they get really eager and go, oh, I can probably help you. I know a lot about Home Depot stuff. Okay. Could you tell me which aisle the elevator bolts are on? And they give you this like, I know he said words. What did he just say? I said elevator bolts, because most people have never become acquainted with an elevator bolt. An elevator bolt is, think about it this way, the rail that the elevator goes up and down and stays aligned so that the car doesn't wiggle back and forth, the rail has to be bolted into the sidewall. Think about it this way. If you used regular bolts, the head of the bolt would stick out into the channel of the rail, and the car would go bumpity, 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 bumpity up the rail as it hit the head of all the bolts. So they make a special kind of bolt that has a large diameter head that is very thin, and you screw it in and it recesses into the rail so it does not create an obstruction. And that's called an elevator bolt. So if these like people really want to show their skill at understanding hardware, you throw them a elevator bolt. Where's your elevator bolts?
He'll probably just say aisle 8.
No, you know what they're going to say? Either, I don't know what an elevator bolt is, or this is a single-story building. We don't have an elevator. Or I think they're over on aisle 8. I only manage aisle 6.
Yeah, or if you ask someone something that is metric, they go like, what?
Oh, no. They know where the drawer is for all the metric stuff, the little metal slide drawers. Here's all our metric stuff.
Yeah,
yes,
right.
But if you've got the M24 by 1, all our stuff is there. Okay.
Well, when I was trying to do some kind of experiment and use stuff like that, and then I go and explain, because they insisted in trying to help me.
Yeah.
And they go like,
sometimes you get a guy who knows what he's doing.
No, I don't. Bye.
Yeah.
There are people there who help you out. They're pretty sharp sometimes. You know, I come to them with a crazy project, and they say, oh, yeah, I got an idea for you.
Yeah. Before they closed up, because they were not making the revenue they used to make, and the seniors at the company got beyond retirement age. They got a little up in the tooth, but there was a Do It Best, kind of a knockoff to True Value or Ace, that was in my neighborhood, and I would go in there all the time. And if I talked to one of the young kids in the family, can I help you? No, I don't think so. And then they'd try, and father or grandfather were over behind the counter, and they'd just look over at him and shake their head like, don't try and help him. And I would turn it back the other way around, and I'd go find what I needed to find, because I knew where the stuff was in the store, and I'd bring it back to them, and I'd say, you see this? I'm using this on a telescope. So if anybody ever says, I need the Vixen dovetail bolt, tell them this is the kind of bolt they need. Okay. But the one that really threw them for a loop was when I said, I need some painter's tape, the blue kind, but I don't want to pay a lot for the 3M kind. Where is that? And he showed me where it was, and I said, good, this will work fine. The generic Do It Best blue tape. Is this the widest you've got? He goes, no, we've got wider. I said, okay, show me the wider. And then he showed me the wider, and I said, I'm going to be using this as the base covering on the build plate for my 3D printer. Oh, you want to paint your 3D printer? No. I'm going to stick it down so I can put glue stick on top of it, 3D print something, and that way I can just peel the tape off and it doesn't stick to the metal bed. And the eyes glaze over. Like, okay, just remember, if somebody comes in and says they need tape for their 3D printer, this is what you show them. Okay.
Frog tape. I love frog tape.
Yeah, the Frog brand tape is not bad. I've also used the Gorilla brand tape.
That's potent
yeah.
stuff. Gorilla tape. Yeah. I got a couple of rolls here.
Yes, I've got a roll right here, actually. Actually, right here. Black Gorilla tape.
I've also got the thinner, narrower.
No, I needed the wider because I used this to build the ultraviolet light sealed enclosure for my 3D printer when I put it in laser mode. Because it's got a very near UV laser. And I didn't want that light leaking out into the room. So I had to seal it